Okay, this is the second page of the group work, and it follows the first page, which is on SONA. And part of the difference here is how the mathematics is represented. The mathematical structure behind designing plate work, knots and links, is analogous to that of the SONA with the plated algorithm. So the first thing you kind of need to do is to watch these videos on how to make the knots so that you can do the experiments. And the basic idea, just to review that, is that we're using a grid of squares, and at the center of each square is a circle, and these circles that I'm shading in mathematically serve the same function as the dots in the SONA. So, and then there's a secondary grid of hollow circles that doesn't have a mathematical structure, but it's an aid to constructing the design. So this is the structure onto which we execute an algorithm. And this algorithm, which is presented in one of these links, is from this guy, like Dave Nichols, who shows us how to draw knots on this grid. It's an algorithm where we start filling in these parallel pairs of lines. Notice how they're at 45 degrees, and they concern 4 circles, 2 solid, 2 hollow. And the idea is you just alternate the direction of the lines, and you fill in all that you can. And then, again, if you watch the video, you'll see you can see examples. He's very good at explaining it. So then we can fill out the edges. And the idea of this is it allows us to construct examples really easily. So there's an example of a 2x3 knot. It's a knot because it's monolinear, just like a 2x3 Lusona would be with the plated algorithm. So we set up a grid. We have this of squares. In the center of the squares are these shaded dots, the primary grid. We have this hollow dots here, which are the secondary grid. And on to that, we execute this algorithm of parallel pairs and rounding corners, and the result is a knot. So you can kind of think of the grid of squares as almost being a program that gets executed by a computer, especially if you know that the historic use of the word computer is a person. If you go back, oh gosh, now it's 70 or 80 years, a computer was literally a person before they were digital analog machines. So what we're seeing here is the result of the design. It's already been done. The structure has been lost. We're going to figure out what's the program, what's the grid. And so here's how we do this. Oh, actually, I should do number 8 first. A 3x3 knot. So the thing to remember with this is that in terms of the Lusona, a 3x3 Lusona rather, it would not be monolinear, right? That's the basis for the tortoise. And I'll make the 3x3 plate work. I use the word plate work, the term plate work, to refer to both knots and links, because these all have the appearance of being plated, woven together. So here's a 3x3 grid of boxes with no break lines, and let's make the knot, and then we'll also look at the corresponding Lusona and how using SONA can help us solve some of these problems as well. So now I just finish up with the corners. So I really am just I'm not having to pay attention to the whole structure here. I'm just filling this in. So there we go. There's the design. Now the analogous Lusona, which we execute differently, it's a different algorithm, has 3 pieces. A knot is monolinear. So how do we make this monolinear? Well, we use break lines. Now it's a little easier to experiment using a Lusona, because they're quicker. They're quicker to do. So here's my 3x3 grid again. And I know not all of you may not have a lot of colors. But you could use a pencil. You know, you could use a pen. You could do some dotted lines to differentiate the different pieces. The idea of break lines, as you would have seen in videos before, is that if you cut across two different components, you'll decrease the number of components by 1. So if I cut across this pen loop, and this is dotted loop, and then I cut across this pencil loop and this dotted loop, those two break lines will result in a Lusona that is monolinear. So the Lusona, because it's faster to do, we can run an experiment on it. Well, it's faster to do, I guess, if you feel confident doing it. If you don't feel confident in doing Lusona, then it's not. That was monolinear. Now I can go ahead and try this with a knot. And the idea is that through all this productive doodling, that you become more comfortable with these ideas, and you don't always have to execute them. That rather you can be confident in your hypothesis. But you can only really understand these things if you do some productive doodling. Remember that the amount of time you've spent on this is relatively new. If you're having difficulties, it's not because of some innate issue with you in mathematics. It's just because it's a new topic. Whether it's a new type of music, or a new type of craft, or a new language you're learning, new things are harder. Okay, where are these break lines? Well, they're between these primary grid points. They would be right here. I'm going to pause the video here to pour some hot water on my coffee. Alright, we're back. So I've put in these two break lines, and let's fill it out. So I'm just filling in all these parallel pairs, and then the break lines prevent me from filling in pairs down there. So before I get there, let's fill on the sides here. It's a little harder to tell from the process of making the knot whether it's going to be monolinear, but we'll check it. So what do I do down here? Well, if this band is coming into the corner, it can't leave the corner, it can't go through the break line, so it has to turn around. So it's constrained, which kind of makes sense if you think about the analogous Lusona. Same thing down here. There's nowhere for the band to go but back out. So they look the same, they should. And now if I were to take and trace this, and this is worth doing to build some understanding, if I were to kind of go along this strip and see if I can do the whole thing, and I can. So this is monolinear, it's a knot. Now, a couple of things from these constructions that we should see by now. Notice that these knots have gaps. There is spacing in between the bands. And the spacing is due to this primary grid and also due to the hollow circles, the secondary grid. The secondary grid, though, is responsible for these indentations. Right? So when we look at a knot or plate work like this, right? These divots, if you will, are going to be the result of this secondary grid. And those that secondary grid, and if you look at these other examples, there's a column of those So there should be some more secondary dots, right? So this gap is due to 1, this gap is due to 1, this gap is due to 1, but these gaps, well, this is a column of gaps in between these columns of hollow dots. So this would be the result. This would be the result of solid dots. And knowing the difference between these things is going to help us decipher this piece of plate work. So 2 with this 2 right here, right? A column of 2, 2, a column of 2, right? A column of 2. So this is 2. So 2 rows by 1, 2, 3, 4, right? By 4 boxes. A 2 by 4 grid is not monolinear. It'll have 2 components. And I'll do this. Well, I won't do this one because I just did one. I recommend doing this. Let's talk about what an answer would be. An answer would be a separately drawn grid, right? With any break lines drawn out. You don't have to shade these dots in like I do. I just do it so I can refer to them. But your answer should be something that a person could execute. If I gave this to somebody who knew how to do this, they should be able to fill it in and get this as a result. Alright, so let's do another one. So this one, same thing, divots, right? A little harder to tell on the side now because these ends aren't the same. There's something going on there we'll get to in a minute. Notice that there's some gaps right below, and in between these columns of hollow dot secondary grid, you would have, this would be 2. Right? You'd have 2 of these solid ones. So you must have 2 here as well. So why the gap? Right? There must be a break line. So again, what I'm doing right now does not qualify as an answer. Not an answer. But rather, this is a 1, 2, 3, 4. This is a 2 by 4 grid. We would just draw over here a separate grid with all the circles necessary and the break lines so that somebody could execute that. Alright, so that would be an answer. Let's do a couple more. You can probably do that one now. Let's jump to something like this. Again, looking at indentations. Here are my hollow circles. But now I've got a couple more. I have 4. Well, the hollow circles, right, they always number a bit more, right? I have 1, 2, 3, 1, 2, 3 of these solid circles, the primary grid, the number of boxes. These hollow circles, 1, 2, 3, 4, they're always a bit more. So 1, 2, 3, 4, this is probably going to be a 3 by. And in between that, you can see there's a stack of 3 gaps right there. Those indicate there's 3 squares. So what about what's this? Well, this is in the column of hollow circles, so there must be a break line between these hollow circles. And what about this? Well, there must be 3 solid circles here and break lines between them. So I've scribbled enough on this. Let's take a look here. This is 3 high and 1, 2, 3, 4 long. So this is going to be 3, 1, 2, and so I draw my primary grid. It'd be better to draw these a little larger, actually. And I put break lines where they go here, and break lines where they go there. Now the other break line I can't put until I put my secondary grid in. So I'll do that. And then really emphasize where that is. Okay, I'm running out of time in this video, so I'll do the other knots in another video.